Okay, so like I said, we want to make sure everyone destroys this midterm. So as I mentioned, monotone convergence theorem, pretty important. Let's talk about that real quick, and then we'll do an exercise on that. So the monotone convergence theorem, there's basically two versions. So the first version would be if xn is an increasing sequence which is bounded above, then the limit exists. If xn is an increasing sequence which is bounded above, then the limit exists. So what's another common way of saying the limit exists, in case this is what the midterm asks of you? What's another way someone would commonly say the limit exists? Yeah, so the limit converges. So you could also just say xn converges. So depending on the wording you see on your midterm, these two things mean the same thing. Okay, and the second version of the monotone convergence theorem if xn is a decreasing sequence, which is bounded below, then the limit of xn exists. And another way to say that is just xn converges. So those are the two versions of the monotone convergence theorem. One is for increasing sequences, one is for decreasing sequences. So we're going to go through an exercise. The exercise we're going to do follows a very standard procedure for monotone convergence theorem questions. Almost every, not every, but almost every monotone convergence theorem question follows basically the same 2 or 3 steps. Okay, any questions so far? Okay, so this is, what section is this? 3.3. Okay. So, section 3.3, question 3? Question 5. Question 5. So it says, let y1 equal the square root of p for some p greater than 0, and let y sub n plus 1 equal the square root of p plus yn. the question says, show yn converges. And it gives us a crucial hint. Okay, so one upper bound is 1 plus 2 square root of p. Okay, so this probably won't happen on your midterm, I'm not sure, but so you probably won't get a hint that tells you one upper bound is this or one lower bound is that. But when you have a recursively defined sequence like this, right? It gives you the first term, maybe the first two terms, and then it defines the remaining terms in a y sub n plus 1 as a function of yn type of fashion. It is very, very likely that you are in a monotone convergence theorem situation, okay? Recursively defined sequence means monotone convergence theorem, usually. Okay, and so they give us this hint. One upper bound is 1 plus 2 square root of p. So we have two versions of the monotone convergence theorem, and this hint is pointing towards one of the two versions. So which one do we think? The first one? Okay. Guys, this class is segregated by gender. What is going on here? Cooties! No. Okay. Okay, let's do this. So like I said, these kinds of questions follow a very, very standard procedure. So when you have a recursively defined sequence, we're going to write this. We're going to go here. So this is what you're going to want to do. So if you're given a recursively defined sequence, a recursively defined sequence, then we're using the monotone convergence theorem. And this is going to basically be in 3 steps. So step 1, show the sequence is bounded. Okay, so if you're using the first version of the monotone convergence theorem, we're going to show it's bounded above. If we're using the second version of the monotone convergence theorem, we'll show it's bounded below. Okay, this step is almost always done with induction. That is almost always how this step is done. Second step. Show increasing or decreasing, depending. Okay, so again, increasing in the first version of the monotone convergence theorem, decreasing in the second version. Okay, so this is just going to be some arguments with inequalities. So then step 3, now we know it's bounded, we know it's increasing or decreasing, so now we invoke the monotone convergence theorem. converges. And I said 3 steps. We're going to add a 4th one. Fourth one, we're going to turn the recurrence relation into an algebraic equation to solve for the limit. Okay. Turn the recurrence relation. Recurrence, how do you spell that? Is it 2 C's? Okay, I don't know, this might be spelled wrong. Actually, it's like definitely spelled wrong. Okay, turn the recurrence relation into an algebraic equation to solve for limit. Okay, so these steps just abstractly written in this way might seem a bit confusing, but once we work this example, you'll see how everything shapes out. Okay. So let's do this. Okay, so we're going to do it on the problem I wrote on the board over there. Okay, so let's get into the solution here. Solution. Okay, so step one, show it's bounded above. Okay, and the question gives us an upper bound. So we're going to say we're going to show it's bounded above by this upper bound. So 1 plus 2 square root of p. Okay, and this is an induction situation. Okay, so for induction, what's the first thing we do? What's the first thing we do for induction? Base case, based. Okay, so base case. N equals 1. So it's given that y1 is equal to the square root of p. Okay, and if you take a number, a positive number, and you double it, you get something larger. And then if you add 1, you again get something larger. Okay, base case done. Now the inductive step. So here we're going to assume it holds for yn. Assume yn is bounded above by this 1 plus 2 root p. I want to move on to a different board, but I'm just going to give everyone like a minute to catch up because I want to cover up the thing I just wrote. Okay, is everyone caught up in their notes? Cool. Okay, so inductive set, we're going to assume yn has this upper bound. Where should I write now? I'm going to write this empty space here. Then, y sub n plus 1, again, this is defined as the square root of p plus yn. And how did this argument go? Okay. All right, this was a pretty interesting argument, actually. So we're going to start by isolating for yn plus 1. So y sub n plus 1 squared minus p is equal to yn. Now, this yn is less than or equal to 1 plus the 2 square root of p, 1 plus 2 square root of p by the inductive hypothesis here. And now we're going to rearrange. So we're going to take this minus p and add p to both sides, and we get y sub n plus 1 squared is less than or equal to 1 plus 2 square root of p plus p. Okay? And now the super clever observation here is that this is exactly 1 plus the square root of p squared. Okay? So this implies, so we have this squared, the squaring function is increasing for positive numbers. So we take our square roots, and we get y sub n plus 1 is less than or equal to 1 plus square root of p. And again, if you just double a positive number, you get something larger. So this is rounded above by 1 plus 2 square root of p. Okay? So we showed yn plus 1 also has this upper bound, and step 1 is complete. Step 1 is complete there. Okay, and this is going to be the hardest step. So we did step 1 here. So any questions? The rest is a little bit easier, I think. Okay, so show that it's increasing or decreasing. This will be a lot easier. Where should I write this? I'm going to try to keep as much of the problem up on the board at once as possible. It's already here. So step 2, so show yn is increasing. Maybe the solution I wrote here for why it's increasing doesn't work. This is greater or equal to yn plus 1. It's greater or equal to square root of He thinks I made a mistake in my notes. But it's okay. Maybe we'll just come back to that step later. That's very cool. Okay. Yeah. I think I made a mistake in my notes, but maybe I can solve this. Okay. We're gonna skip step 2 for now because I think I made a mistake. Okay. Show yn is increasing, so that's meaning you're gonna show yn is less than or equal to yn plus 1. So you're gonna do this. I did not do this correctly in my notes. So maybe we're gonna come back to step 2 later. But just for the sake of flow, let's assume we've done this so you guys can just see the process. Step 3, we're gonna invoke the monotone convergence theorem. Okay, so yn is bounded above and increasing. Yn is bounded above and increasing. So yn converges by the monotone convergence theorem. Okay, so that's step 3. And let's do step 4. Again, we'll come back to step 2. So, step 3, step 4, turn the recurrence relation into an algebraic relation and solve for the limit. Okay, so what this looks like is we're going to denote the limit. Now we know the limit exists, so we can denote the limit by L. Then, so this is going to be a few sets here. L is equal to the limit of yn. And in fact, let's go ahead and do this right at the start. This is equal to the limit of yn plus 1. And let me quote a theorem from the textbook for this. In my last tutorial, I just wrote this down, but then a student pointed out that this is actually worthy of quoting the theorem. So let me just find the theorem here. Here you go. Theorem 3.1.9. So this is theorem 3.1.9. Okay, so you don't have to, on your test, you don't have to cite this theorem, but I'm just doing it for the sake of completeness right now. Okay, now we're going to use the recurrence relation. So this is equal to the limit of the square root of p plus yn. Okay? Carrying on here, we're going to put the limit inside the square root. square root of the limit of p plus yn. Okay, so let me again cite a theorem from the textbook. This would be theorem 3.2.10. So theorem 3.2.10 is telling us we're allowed to interchange limit and square root. Okay, and now we're going to distribute this limit over the two summads. So the limit of the constant function p and the limit of yn. Okay, so we're allowed to distribute limits over sum. This is theorem 3.2.3. Okay. This is equal to, okay, so this first limit, where it's just a constant sequence that always takes on value p, what's the first limit there? That always takes the value of p. We have two limits in the square root. What does the first one converge to? Yeah, okay, p. So this first piece of the limit is just p, and here we have the limit of yn. That's L. So plus L. Okay, good, we like this. And so now we're ready to finish it up. Okay. So what we've shown is the limit L satisfies this algebraic equation. And we just solved it with the quadratic formula. So this is L squared equals P plus L, which tells us that L squared minus L minus P equals 0. And the quadratic formula then tells us that L is equal to negative B, so minus 1 plus or minus B squared, that's 1, minus 4 times A, that's 1, times C, that's minus P. Divided by 2A. Okay? So this becomes minus 1 plus or minus 1 plus 4p, the square root of 1 plus 4p divided by 2. Okay, so now we just need to decide whether it's going to be the positive branch or the negative branch. And let me just write a justification for that somewhere.
Shouldn't it be positive 1? Because it's minus b.
Yeah, it should be. Thank you. Plus 1. So you passed by test. Square root of minus 1, bonus marks to you. Okay, and then we just have to decide which branch this is going to be. If we're going to take the positive branch or the negative branch. And I'm pretty sure it's going to end up being the positive branch. I'm pretty sure one of these should always end up being negative. Yeah, one of these is negative. Okay. So I don't want this to drag on too long, so let me just go back to this board. Okay, we'll talk about step 2 in a moment. Okay. So what we know is L is equal to 1 minus the square root of 1 plus 4p over 2, or L is equal to 1 plus the square root of 1 plus 4p over 2. So 1 minus the square root of 1 plus 4p over 2. This is going to be negative. Okay, so I'll just tell you to justify this. It shouldn't be too hard. This is pretty straightforward, but I just kind of want to finish up. So this is going to be negative, yet our sequence is strictly positive, right? Because we started with the square root of p was our first term in our sequence, and then it's increasing after that. y2, y3. Okay, so we can dismiss the negative root. So we conclude that our limit, our L here, L is the limit of our sequence, is exactly this, 1 plus the square root of 1 plus 4p divided by 2. Okay, so again, there's this step 2, which I kind of mucked up, which we'll come back to in a sec. But let's just internalize this for now and see if we have any questions.
If this was on a test, could we have just stopped after step 3? Because the question just asks to prove it can show it converges. Or does that have to mean that we have to show the limit?
I think I might have miswrote the question from the textbook. The textbook says show it converges and find the limit. I think I maybe just forgot to write that. Now, if it says show it converges, then yes, you can stop at step 3. If you're only asked to show something converges, you do not need to compute that limit. But in this case, I think I just miswrote the question. In this case, we are asked to also compute the limit. Good question. Thank you very much. Okay, so this might seem quite intimidating if it's your first time seeing this sort of process. But just do the practice problems and you'll feel better soon. Okay, let me just quickly see if I can find something on math stack exchange or something on this step, on this second step. So let's see. Not that. Stack. Okay, AI overview is giving me something. Screen both sides gives us that. Condition is this. Okay. It's 12:06. I did want to do another exercise, but maybe I should try to figure out why this thing is increasing. Just give me 2 minutes to see if I can justify the increasiness of this sequence. Quadratic. Rewrite it this way. Okay. Okay, I'm not going to try to improvise something here. So I looked that up a little bit, and that gives you something fun to do in your homework. Figure out why this sequence is increasing. Okay, so we have 13 more minutes, and the goal is to make sure everyone freaking kills it on the midterm. So is there anything like anything we're concerned about, or any questions we have about the midterm right now? Anything in particular we would like to review? I do have another, I have a bunch of other questions prepared to show you guys. I have another monotone convergence theorem question ready to go, but that one's quite involved. Okay, so you will want to have a good understanding of supremums and infimums, limit laws, for example, as dictated by theorem 3.2.3, and the monotone convergence theorem for your midterm on October 21st. Okay, so I suppose we could do a supremum infimum question, or a limit laws question. Maybe I just blast through another monotone convergence theorem question. Let's do that. That seems fun. Okay, one more MCT question. Okay, this one is question. We're gonna blast through this one. Question 10 of, what was the section of 3.3? Okay. 3.3, question 10. So this question is just saying converge or diverge. And it gives us this sequence. So this sequence is y sub n is equal to 1 over n plus 1 plus 1 over n plus 2 plus dot 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 plus 1 over 2n. Okay, and this is going to be for n greater or equal to 1. Okay, so converge or diverge, and let's do the solution. Solution, so this converges by the monotone convergence theorem. So two things to do: show it's bounded above and show it's increasing. So let's do bounded above. Okay, this is a kind of a fun argument. So what we're going to note here is that n plus 1 is less than n plus 2 is less than dot 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 less than 2n, which implies what I like to call a flippy-do. 1 over n plus 1 is greater than 1 over n plus 2 is greater than dot 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 is greater than 1 over 2n. Okay, so of all the terms appearing here, the greatest term is 1 over n plus 1. So, we have yn equal to 1 over n plus 1 plus 1 over n plus 2 plus dot 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 plus 1 over 2n. Again, as we just showed here, each of these terms is bounded above by 1 over n plus 1. Okay, so each term is bounded above by 1 over n plus 1. So let's use that bound. So we have 1 over n plus 1. Here, let's replace this guy with 1 over n plus 1. And what we have here, we're just adding a whole bunch of, wait, I'm about to show it's bounded below. That's not what I want to do. I want to show it's bounded above.
You just need to flip that inequality. The one in front of the 1 over n plus 1.
The 1 over, okay, yes, but I think that I'm about to do, okay, right. So all of these guys, let me see if I follow you. Everyone is bigger than 1 over 2n, is that, oh wait.
No. So 1 over n plus 2, for example, is less than 1 over n plus 1.
Right, okay, I just wrote it wrong.
Yeah.
Thank you, oh wise one.
Don't mention it.
So you get another square root of minus 1 bonus marks. However, square root of minus 1 squared is minus 1. You lose a bonus mark. You get minus 1 marks. Okay, thank you. So we got 7 minutes. Let's do this thing at supersonic speeds here. Okay, so each of these guys is less than 1 over n plus 1, so we get one of these. We just replace everything with 1 over n plus 1 at the expense of introducing this inequality here. Now, how many 1 over n plus 1s do we have here? N? Is this a new gang sign I'm not familiar with? Okay, so this is exactly n times 1 over n plus 1. Okay? And n divided by n plus 1, that's less than 1. Good. Okay. So, an upper bound is 1. Good. Now, so we found it's an upper bound. Now we need to show it's increasing. This step is super fun. Okay. This step is so fun. So let me write down what y sub n plus 1 is. Y sub n plus 1, this would be 1 over, so the other guy is n plus 1, so this is n plus 1 plus 1 plus 1 over n plus 1 plus 2 plus dot dot dot. Okay, and let me write a few terms before the last final term. So n plus 1 plus n minus 1 plus 1 over n plus 1 plus n, and then the final term is 1 over n plus 1 plus n plus 1. Right, so this is our 1 over 2 times n plus 1. Okay, so this is the expression for y sub n plus 1. So we're starting at n plus 2. And what I'm going to do, I'm going to do a sneaky little trick. I'm going to add 1 over n plus 1, and then I'm going to immediately subtract it, so that does not change anything. Okay? And what we notice here we have our n plus 1, here we have our n plus 2, n plus 3, up until here, where we're getting our 1 over 2n. All of these terms add up to y sub n. Okay? So what we in fact get, add all of those up, we get y sub n, and then what's left is these guys. So plus 1 over, so this term is going to be 2n plus 1, plus 1 over, that term is going to be 2 times n plus 1, and then minus 1 over n plus 1, like so. Okay. So sneaky little trick there, very sneaky trick. And now we just want to show, okay, so we want to keep making this bigger. Okay, so 1 over 2n plus 1, that's the bigger number. I always get confused at this kind of thing. I got this. 2n plus 1. That's the bigger quantity. Less. Okay. So here's the bigger quantity. Okay. So this is greater than, so this term is greater than this term. So y sub n, and I'm going to, and then at the expense of this inequality, I'm going to just turn both of these guys into this guy, the smaller term here. So plus 1 over 2 times n plus 1, plus 1 over 2 times n plus 1, and then minus 1 over n plus 1. So we have 2 of this term twice. So this is our y sub n plus 2 times 2 over n plus 1 minus 1 over n plus 1. And these 2's cancel out. 1 over n plus 1 minus 1 over n plus 1, we're just left with yn. Okay, so what we showed here was that yn plus 1 is greater than yn, aka increasing, and then, I don't want to keep you too long, but increasing, so use monotone convergence theorem and we're done. Okay, alright, that's how it works. That was, I don't want to keep you guys over the allotted time for the tutorial, so that's how that one goes. Okay, any questions for today? No questions? Okay, you guys have your midterm, October 21st, after reading me. Do the assigned practice problems. Get good at supremums and infimums. Get good at limit laws as dictated by theorem 3.2.3. And get good at monotone convergence theorem. And you will thank me. Okay. All right. Have a good reading week.